All right, let's jump right into this explainer. Today, we're looking at a fascinating real-world David versus Goliath story in the tech space. We're talking about the truly insane engineering behind the 1.6 trillion parameter DeepSeek V4. We're going to break down exactly how a highly constrained team managed to pull off what a lot of people thought was just completely impossible. Let's map out how they engineered this absolute masterpiece step by step.
The sheer contrast here is staggering. On one side, you've got the top closed AI labs, right? These are massive teams burning through billion-dollar budgets with basically unlimited computes. And then, on the other side, you have the DeepSeek team. They're roughly 40 times smaller than giants like OpenAI. They're incredibly constrained on hardware, and get this, they don't even have access to the absolute top-tier NVIDIA chips. Yet they are somehow beating the giants at their own game on a shoestring budget. It's wild. And the scale of what they built is literally mind-blowing. We are talking 1.6 trillion parameters. Now, if you aren't super technical, just think of parameters as the tiny dials and knobs inside the model's brain that store everything it knows. Generally speaking, more parameters means a smarter model. But stacking 1.6 trillion of them, that creates an absolute engineering nightmare for training and stability. So the big question is, how do you actually keep a 1.6 trillion parameter brain from just collapsing on itself? Well, to make things even harder, DeepSeek V4 pairs that massive parameter count with a 1 million token context window. Think of this as the model's short-term memory. A million tokens is basically 750,000 words. That means you could feed it the entire Harry Potter series, ask for some obscure, tiny detail buried on page 432, and it just flawlessly recalls it. For us, the users, this means AI agents that can actually do your taxes or code an entire app without ever losing their train of thought. But to really understand the brutal memory battle they had to fight to achieve this, we have to look at something called the KV cache. See, an AI doesn't just read text. For every single new word, it has to compare it to every single past word to understand the context. It stores all these intermediate results in the KV cache, which is essentially a massive running lookup table. At a million tokens, this becomes a downright brutal compute bottleneck. It's a lot like your own computer completely running out of RAM and crashing. You end up with gigabytes of data just sitting there hogging expensive GPU memory to maintain context for a single prompt. It normally chokes even the highest-end hardware. So the really crucial point is how they actually bypassed this bottleneck. Instead of just throwing brute force compute at the problem, which, remember, they didn't have, they asked a smarter question. How little can we process and still understand everything? And to answer that, they built this brilliantly elegant four-step hybrid attention architecture. First up, compressed sparse attention, or CSA, groups 4 tokens together into a dense summary. Second, a lightning indexer rapidly scores these blocks, picking only the most relevant ones to actually process. Third, heavily compressed attention groups huge chunks, like 128 tokens, or about a whole paragraph, into one single summary for broad context. And finally, a sliding window keeps the most recent words completely uncompressed for perfect immediate recall. Honestly, it's exactly like how you'd study for a huge exam. You don't constantly sit there and reread the entire textbook cover to cover, right? You keep the last few pages open right in front of you, which is the sliding window. You rely on broad chapter summaries to keep the big picture in your head. That's the heavily compressed attention. And when you need a highly specific detail, you just search your highlighted sections, and that's your lightning indexer. They basically took a very intuitive human strategy and turned it into a highly precise mathematical system. And the efficiency payoff here is just insane. When you compare it to their previous V3.2 model, which honestly was already considered super efficient, DeepSeek V4 Pro requires 3.7 times lower flops. That means it runs on basically 27% of the compute. But even more incredibly, they reduced the KV cache memory footprint by a staggering 90%. They essentially shrank the short-term memory requirement down to just 10% of what it used to be. It is an absolute magic trick of engineering. But here's the thing, memory was only battle number 1. The stability battle is where things get truly terrifying. When you stack dozens of layers together at a 1.6 trillion parameter scale, the mathematical signals flowing through the network start to naturally amplify. It's exactly like a microphone placed way too close to a speaker. You get this screeching runaway feedback loop. In our neural network, this is called a signal explosion. The numbers just blow up to infinity and boom, your incredibly expensive training run completely crashes. Traditional bypass lanes just weren't enough to stop this at the trillion parameter scale. So they invented something called Manifold-Constrained Hyper-Connections, or MHC. Instead of trying to put out the fire and dampen the mathematical explosion after it happens, DeepSeek enforces a hard mathematical rule before it can ever occur. They force the connections to act as what's called doubly stochastic matrices. Now, don't let the math jargon scare you off. In plain English, this just means every row and every column of numbers must mathematically sum to exactly 1. The total signal is strictly conserved. It can literally never blow up because the math outright forbids it from happening. Now, enforcing that hard mathematical constraint means running a super complex 20-step loop called the Sinkhorn-Knopp algorithm on every single layer. That sounds like it would completely ruin their efficiency, right? But by aggressively custom tweaking the low-level GPU computations, they actually got that massive loop down to a tiny 6.7% runtime overhead. Adding a 6.7% compute tax might sound a bit annoying, but trust me, it's an absolute bargain for an ironclad insurance policy against your multi-million-dollar model spontaneously crashing. So, with stability totally locked down, they had to rethink how the model actually learns. They completely ditched the industry-standard training algorithm AtomW for a custom optimizer called Muon. Muon learns in this really clever two-phase process. First, aggressive convergence comes in and makes these big, rough adjustments. Then, careful stabilization takes over and makes tiny, precise tweaks. Think of it exactly like tuning a guitar. You crank the tuning peg to get close to the pitch really quickly, and then use very subtle, tiny movements to dial it in perfectly. This two-step dance allows the giant model to learn so much faster while staying perfectly stable. But, all these elegant equations don't mean a thing if the hardware itself isn't perfectly synchronized. A 1.6 trillion parameter model cannot fit on one machine. It spans thousands of GPUs across entire data center racks. And every single millisecond a GPU sits there waiting for data to arrive over a network cable is just wasted money. To fix this, they perfectly choreographed the data transfer. They broke it down into sequential waves. While the GPUs are actively crunching the numbers for wave 1, the data for wave 2 is already traveling over the network. Communication and computation are so perfectly overlapped that no hardware ever sits idle. And to guarantee this microscopic data center choreography worked flawlessly, they had to be unbelievably meticulous. When you have extremely limited funds, you really can't afford to just guess and check. They wrote these things called fused kernels, which is basically merging multiple math operations into single commands using a specific language called tiling. But writing this stuff by hand is incredibly error-prone. So instead of just crossing their fingers and hoping it worked, they used a Z3 SMT solver. This advanced tool allowed them to mathematically prove with 100% certainty that their code was entirely flawless before they ever hit the run button. Okay, so now that the architecture was totally flawless, it was time to feed the beast. They trained V4 Pro on a staggering 33 trillion tokens of data. Now, if you throw all of that at a brand new model all at once, it just drowns. So they used a curriculum timeline. They started small, giving it 4,000 token sequences just to learn basic grammar and structure. Once it was stable there, they expanded to 16,000, then 64,000, all the way up till the full 1 million token window. They very slowly expanded the model's working memory while it was still actively learning how to think. Even with that super careful timeline, though, massive models can still experience these things called loss spikes that completely derail training. DeepSeek's weird but absolutely brilliant solution to this is anticipatory routing. When the model detects early signs of instability, it temporarily stops looking at its current, chaotic state and instead routes decisions based on slightly older, historical snapshots of itself. It's exactly like using a moving average on a stock chart. It ignores the daily chaotic noise and just locks onto the smooth overall trend until the danger passes. It essentially makes the model completely self-stabilizing. All of these incredibly clever workarounds, the hybrid attention, the constrained hyperconnections, the fused kernels, they all culminate in jaw-dropping results. Just look at this number, 120 out of 120. That is a completely perfect score on the Putnam 2025 benchmark. For context, that is a math test that humbles some of the smartest human undergraduates in the entire world. It showcases a genuinely unprecedented level of frontier reasoning. And when we zoom out and look at the broader benchmarks, it absolutely proves this architecture is a true heavyweight. Across knowledge, reasoning, and agent tasks, it consistently matches or outright beats top closed models. It is maintaining a higher head-to-head win rate against Anthropic's Opus 4.6 Max, and it's also edging out Google's Gemini 3.1 Pro, even when pushed to the absolute extreme limit of its 1 million token retrieval window. Which leaves us with this final, lingering thought. We just walked through how a team that is 40 times smaller, without the absolute best hardware, engineered elegant mathematical solutions instead of just brute forcing the problem with billions of dollars. They built an absolute masterpiece, and then they released it open source for free. So if doing vastly more with vastly less yields these kinds of incredible top-tier results, what exactly happens next to the industry giants who are relying on closed trillion-dollar monopolies? It is a fascinating question, and one that changes the entire landscape of AI going forward. Thank you so much for joining me on this explainer, and I will see you in the next one.